In the second part of the discussion of concurrent Erlang, what we will do is talk about how processes can be given names, and talk a bit about how we can apply timeouts to the processing of messages, and make some general remarks about how processes tend to look in Erlang. What we did in the first part of the session was to talk about how processes were created using the spawn BIF. Remember, BIF is the Erlang terminology for a built-in function. That is a function that we can call without mentioning which module it comes from. So spawn is the BIF we use to create a new process which will run code from a particular function in a particular module. And we pass messages between these processes which don't share memory. We pass messages by using PID bang message or PID pling message, the exclamation mark symbol. On the left of that is the process identifier, which we get back as a result of spawning a process. And that's the way that we get hold of a handle on a process. And then the receive statement, where we have a number of clauses which can selectively process messages which are stored in a mailbox for a process when they're received. Reminder just that process message passing is asynchronous. A message is sent. It doesn't have to be processed before the sender can carry on and do other things. And processes will store messages in a mailbox until they are processed. Okay, let's talk a bit about how processes can be named. We do that using the register BIF. That takes two arguments. It takes an atom, which is going to be the name, the alias of the process, and it takes the PID of the process, which is how it is identified. And remember, the PID can come back from a spawn. Any process can register a PID, and once a process is registered, any other process can send a message to it. We can find out what the registered processes are by calling the registered BIF, and we can find out the PID of a process by calling whereis with its alias as argument. Let's take a look at an example of this in practice. We have a process with PID 1, and what we see is underneath that process we see the start code for the process. The first expression to be evaluated is spawn of the server function in the number module with no arguments, and that returns a PID. And then the second statement we execute is a registration. So that new process is now called analyzer, because we've called register with analyzer and PID. You can then see how we interact with that new registered process in the analyze function. And you can see there a message is being sent not to a PID now, but is being sent to that named process, analyzer. And that sends a message and doing whatever, sends some data to be analysed by that other process. But any process now can send a message to that process whose PID was stored in a variable PID, but is now named by that name that's accessible to any other process. You see an example. We said that message sending to a PID never failed. If you send a message to a non-existent PID, it simply gets thrown away. That's not the case if a process is registered. If we send a message to a name that is not registered, we will get an error. We'll get the process that tries to send that message will terminate with a bad arg error. So I have to be aware of that we get the way that you handle a problem like that is different between a non-registered process and a registered process. The next thing I wanted to talk about was how to deal with message reception timeouts. Now let's suppose we're in process with PID B, and we want to receive a message within a certain amount of time. When we come to the receive statement, there may be messages already in the mailbox, in which case we deal with them. But suppose there are no messages in the mailbox when we arrive at that statement, and we want to be certain that we will move on from that statement within a fixed amount of time. What we can do is use the after version of the receive clause. So what we have in this sort of statement is we have receive followed by a number of standard clauses with a pattern and a body, and then we have the after keyword followed by a timeout expressed in milliseconds and code that is to be executed if that timeout is invoked. So if, in this example, we receive a message within the timeout, then expressions 1 will be executed. But otherwise, we'll execute whatever code is there in expressions 2. So we can be sure of processing a message and moving on within a certain amount of time. So here you see an example. This is the analyzer example. We've got a receive statement that if we get a reply message, we simply transform that into an OK message. If we receive an error message, we simply transmit that. But if we receive, we simply return that. If we receive neither of those within a second, then what we do is we return an error tuple together with the atom timeout. So we're effectively finding another reason to fail there. So this analyze function might return the result OK and a value, or it might return an error from the analyzer process, or an error due to a timeout. So we've dealt with that. Now it's possible, of course, that if having a timeout clause means that there are some messages that might not have been processed. They might arrive later. So we have to be aware that those messages will go into the mailbox and will potentially need to be handled at some point. Let's take another look at an example here. This is a function that will send a message after a particular time, and let's have a look at what happens there. What send after does is immediately spawn a process which executes send in the timer module with arguments self, which is the PID of the creating process, a time and a message. And what we have in the body of the send is a receive statement with a timeout, but with no standard processing. So there is no way of handling any messages that come in. All it can do is, after the timeout, send a message to the PID. So there you can see that what this does is send a message after a fixed amount of time. And what you see in the sleep function at the bottom is simply a function that will sleep for a fixed amount of time before terminating. So there are ways of ensuring that if we want to not to send a message immediately, we can use the send after function. If we want simply to do no processing for a period, we can use the sleep. And both of those use this degenerate form of the receive statement where you've got no message processing clauses in there. Now what you see here is as we said earlier on, if you use a timeout, it's possible that you will leave some messages in the mailbox which you don't want to, which you've timed out, so you don't want then to process those messages properly. Here's a nice example of using, again, this timeout mechanism to flush any remaining messages from a mailbox. And let's have a look at this. How does it work? We've got a receive statement which will process any incoming message, and we've got a timeout of 0. So the way that the effect of this will be that if there are any messages in the mailbox, the first one will immediately match, and the effect of that is to call flush. So every time there is a mailbox every time there is a message in the mailbox, we will loop and call the flush function again. If then we empty the mailbox and call flush again, we will time out immediately, there are no further messages, and just return OK. So this has the effect of removing all the messages from the mailbox without performing any action other than to remove them, and then terminate when there are no further messages in the mailbox. So just a reminder of some of the definitions that we've been using. We use the term process for a concurrent piece of activity in the system. And as I said right at the start of this chapter, in Erlang you can run thousands, tens of thousands of processes simultaneously. These are not like operating system threads, they're not like Java threads. These are lightweight processes. They're also unlike OS threads or Java threads in that they don't share memory. Each process has its own memory, which is separately garbage collected. So the garbage collector is very fine-grained and will ensure that on a per-process basis, memory is recycled. So if there is no shared memory between processes, the only way that processes can interact is by sending messages. And that's the way of sending data. The data might be data, or the data might be to help in communication. So in order to pass information about processes, we share their PIDs, and those PIDs are often a component of a message. It's often the return address. So you send a letter to somebody with your address on the back, and they can then send a message back to you using that PID. We talked about timeouts, talked about a process is registered if it is given a name using the register BIF or built-in function. And we said right at the start about process termination. There are two ways a process can terminate. A process will run the code for a particular function. When that function terminates, the process itself terminates. And that's called normal termination. Otherwise, if there's a runtime error, the process will die, and that's called abnormal termination. Now, I just wanted to conclude by talking a bit about what the skeleton of how a whole lot of processes look. It's often the case that a process will have this form. That a process will be started up by calling spawn. So in this example, we're calling the function init from the server module with some arguments. So we start off by calling this init function, and what that does is set up a loop. So looking now in the body of the init function, what do? Well, we call an initialize state function. We somehow set up some state, and then we call loop with that initial state data. The powerhouse of this process is the loop function itself. And what we see there is the body of the loop is a receive statement. And it has two clauses. The second is to handle a stop message, the stop atom. And what that does is we execute some code that cleans up and then terminates. But if we receive a message which has to be handled in some way, what we do is in some way we handle it, calling a function. We've called it handle here, and that gives us back a new state. And then what we do is we call the loop function again, but with that new state value rather than the one we started with. And this maps very well onto the example we saw earlier of the function to keep a running total. What we did in the loop body there was the new state was got by adding the latest number to the running total, and then we called the loop again with that new running total. What we did when we terminated was simply send a stopped message back to the function that had created, the process that had created us. So this pattern of doing some initialization and then sitting in a receive eval loop until you receive a message to stop, at which point you terminate gracefully. That's a very general pattern for how processes in Erlang tend to look. So we've come to the end of this chapter on concurrent Erlang. We've talked the two things we've added to what we talked about earlier were the idea a process can have a name through the process of registration, and also that we can time out in message handling. So we're not forced to wait forever inside a receive statement. And we finished off by talking about the general format that processes had. What I'll do now is just give you a short demonstration of a registered process, and then we'll call it a day. Let's go back to the example where we had a process which would keep a running total of integers that we sent to it. And here we see it. We start off by spawning the main function, and here's the main function that receives either a stop message or an integer. In the integer case, it adds it to the running total and calls itself recursively. This loop, just as I said at the end of the chapter, this is the typical process structure. What we have here are the functions to interact with that process. The add function that sends itself plus a number to the PID of the process that does the addition. And here we have the stop function that does a similar thing. So we spawned this in the start function. We collected the PID from that, and then we use the PID in these two functions. However, if we make this a registered process, we can have a much simpler interaction with the adder process. Let's have a look at what we do. What I've got is are the two versions side by side here. We start off in the same way. We spawn the function in PID, and then we register that PID under the name of adder. And now, once we've done that registration, we can here send a message to adder, and we don't have to pass that PID around as an argument to add or stop. So let's take a look at this in the Erlang shell. We compile it, and then we can start it. And notice we didn't have to capture the result of that in a variable, because we can send messages like add 5 directly, or add of 17, without having to pass in the PID, because inside the body of the add we have the name of the process. And in a similar way we can stop the process just by calling the stop function. And there we are. So instead of having to pass that PID around, we use the registered process there. Okay, that concludes what I wanted to say about processes and concurrency, and so I will stop there.